LearningMeasure.tv, science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 3, Wave Phenomenon Applications. Hello. Welcome to episode 3 of the LearningMeasure.tv podcast. My name is David Archer. I'm the owner of LearningMeasure.com and LearningMeasure.tv. This week we will take the application of the wave phenomena that we talked a little bit about last week and expand it a little bit. And this episode we've got a new sponsor. We're sponsored by GoToMeeting.com and TradePub.com. But first we're going to do a little review of last week. Okay, to review what we did last week, we already know that periodic phenomena, we have the relationship omega, the angular frequency, is equal to 2 pi times the frequency, which is equal to 2 pi over the period. But we already know for wave phenomena from last week that the velocity times the period is equal to the wavelength. From that you can conclude that omega is also equal to kc, or kv, whatever, the velocity. And again, from spatial relationships, k, which equals 2 pi times the spatial frequency, which equals 2 pi over lambda, equals omega over v. That's the relationship between omega, k, and all the other parameters for traveling waves. And a general sinusoid looks like, in one dimension, is e to the I k r, or kx, let's say for one dimension, plus or minus omega t. From that, you can rearrange this, and this is also equal to e to the I k plus or minus, well, you could say x minus vt. Okay, or plus. So this does look like a wave traveling forward or backwards. And then we made the leap to 3 dimensions, which I'm going to go over a little bit more detailed this time because there was a mistake made in the last podcast that I didn't catch. I said it, but I didn't. That's not what I was thinking. Okay, in 3 dimensions, you have some sort of coordinate system. Let's say 3. And you need 3 numbers to specify a point in a 3-dimensional space. Let's say x, y, z. So if you have some point out here, some vector, okay, you need to know, let's say, okay, this would be the height above this point is the, let's see, the z component. This is the x component and the y component. So in general, a 3-dimensional wave, it propagates in a direction. The wave vector is a vector, k. Now if you pick 3 dimensions, 3 directions, one along the x hat, we'll call that vector x hat. Along this direction, we'll call it y hat. Along this z direction, it's z hat. In general, the wave vector is kx x hat plus ky y hat plus kz z hat. Okay. This defines a direction in space, but we also know the magnitude of k, just k, equals omega over c, equals the square root, and you can prove this by applying the Pythagorean theorem a bunch, is just the sum of the squares of the components. But we know it's omega over c or 2 pi over lambda or any of the other number of expressions we have for it. It's also equal to this. Okay, and a general position vector r, describing any position in space, is going to be the form x hat plus y hat plus z hat, 3 components of a vector. Magnitude of r, just we'll write r, the square root of the components, x squared plus y squared plus z squared. Okay, you can prove this using the Pythagorean theorem if you want. It's fairly easy. And then the general form of a plane wave now, I claim, was e to the I k dot r, which is correct. Okay. Now, the mistake I made last week is I don't know why I wrote it that way. A spherical wave is e to the I k r over r, where these are magnitudes, not vectors. Okay, that was the mistake last week. I was thinking magnitude and I wrote vector and said vector. I don't know why. It happens. I should have checked it carefully before letting it go. Anyway, this is the general equation of a spherical wave, and this is the general equation of a plane wave, a sinusoid. Okay, another thing I say real quickly, this could also be written in the form, the wave vector k, in terms of, it can be omega over c times a unit vector in the direction of propagation, which I'll call k hat. Now, we'll talk more about that next week, but this is something that gives you the directions, and this is something that gives you the magnitude. You could write it this way. One more thing, I guess I should define the dot product. It's all you do when you have two vectors, the dot product is the first component times the second component, plus the second component times the second component, etc. So the magnitude r can also be written as the square root of r dot r. Any vector, its magnitude is the square of its dot product with itself. Dot product is just a projection of one vector onto another. Okay. We have a new sponsor, and I'm going to read a short ad for them right now. So, talk about meetings. I don't know, we might have one, try one for a course or something. If you're looking for a better way to present or collaborate during your conference calls, your solution is simple. Web conferencing with GoToMeeting. During your call, everyone logs on to the gotomeeting.com and your computer screen shows up on their computer screens. It's like you're in the same room. GoToMeeting is perfect for sales or product demos, training, I hope, or real-time collaboration. Plus, you're not charged per minute like other providers. You can meet as often as you want for as long as you want. With GoToMeeting, you can meet with anyone, anywhere, without leaving your office. You not only save time, but money too. See for yourself. Try GoToMeeting free for 45 days. Just visit gotomeeting.com/podcast. That's gotomeeting.com/podcast. Try GoToMeeting today. Yeah, give them a try. It will help us out. We might be able to do more of these. Well, in this next section now, we were going to talk a little bit about the history of wave phenomenon. In 1678, this guy here, Christian Huygens, discovered a principle that bears his name on a paper he wrote on the wave theory of light. This guy has a fascinating history as far as I'm concerned. He invented the pendulum clock. He has a patent on pocket watch. He was an astronomer, discovered Titan, a mathematician. Fascinating guy. But he came up with what's called Huygens Principle. And that basically states as if you have a wavefront, some arbitrary shape, and you want to know where the wavefront goes at some time, and you know what the velocity of the wave is. He's saying, well, if you, on each point on the wave, if you put a little sphere around it of, velocity times the time, and you do that for the whole wavefront, that the envelope of all these little spherical wavefronts gives you the envelope of the wave at some future time. Well, that's kind of interesting, and maybe it seems to make a lot of sense. But in the late 1700s, this guy here, Augustin Fresnel, added to Huygens' principle, saying that the field at any point is the sum of spherical waves emanating from the wavefront at some earlier time. So that if you have some wavefront and you had some point in space, you could sum up all these spherical waves coming from the wavefront for that particular point. So this is going to be a sum of things that look like e to the ik, ri, where you're summing up a bunch of over r, right, of over ri. So that you can get the field at this point through a sum like that. And that's come to be known as the Huygen-Fresnel principle. So the basic idea is, and it doesn't have to be a wavefront, it can be any surface actually, just at a prior time. And then you could sum over from each point on that surface what the fields were at that previous time, and you can come up with the field at a point. Okay, what do you do with that? We'll show you as soon as we come back.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
Okay, so now that we have all that, what do we do with it? Well, what if you had some source of something that was emitting some type of waves? Oh, my pen's starting to get a little dry here. Let's try a different pen. Let's see, purple. You have some object. It's emitting some sort of waves, and for purpose of this discussion, it's emitting it in a highly directional manner. Maybe it's electromagnetic wave, maybe it's acoustic waves, but it's emitting it out through some sort of angle, and everywhere else it's zero, and out here it's zero. That's a pretty big assumption, but we'll do that for now. Let's say, like a highly focused beam of light or some sort of highly directional speaker or an antenna, highly directional antenna. Well, first I should mention all waves, even spherical waves, if you can imagine a spherical wave, propagating out, you know, as you get farther and farther from the source, it looks more and more like a plane wave. So if you get far enough out away from the source, the field out here from the whatever that localized source is going to look like some sort of amplitude as a function of the direction, which we're going to call k hat, right? We talked about that a second ago. And that's going to give you a spectrum of plane waves. Well, so for each direction, there's a plane wave associated with it with some amplitude. So one way you can measure the pattern of this is get far enough away so the thing looks, whatever wave type is coming at you looks like a plane wave, and spin the thing around and get an idea of what the pattern of this things look like via, you know, in each direction. But another thing you can do is close in, you could, let's say you measured the amplitude on some plane that captured all the energy. So this plane is big enough, finite plane's big enough, that it encompasses all the energy that's being radiated from the source in this direction. Then you can sample the amplitude at a bunch of points on this plane. Now, if, you know, so each one of these is, let's say, some amplitude a of x, y. Okay, there's the plane here. If you wanted the point, you know, the field here, you could use the, you know, the Huygens Fresnel principle. You need to modify a little bit, but we won't get into that here. So you're going to get some sort of ax, sum over the ax, y, e to the I, k r I. Oh, well, you're not going to be able to see that. That's too small. Anyway, you can sum up from here a bunch of spherical waves. Well, the other thing you can do, if you want a particular direction, k, since these are spherical waves, it puts out pretty much equally in all direction, right, in spherical waves. So the component in a given direction from each point is going to be something like the sum of these axy things times e to the I k dot r. Okay, looks like a plane wave. This is the component of that particular plane wave for that particular point on the surface. Well, this is beginning to look something like what's called a Fourier Transform, or a two-dimensional Fourier Transform. This is going to be some of the discrete Fourier Transform, e to the I kx x plus ky y. Okay, that's the sum over all the elements in this plane. Turns out this gives you this. And this is the same thing you could have measured in the far field by spinning the thing around and looking, you know, what the relative components of each plane wave is. So this is the basic idea behind near field measurements, which is going to be the topic of next week's podcast. Now, this gives you the direction, this plane wave, the pattern in the forward hemisphere. If you did the same thing back here to the backside, you get completely the wrong answer. And there's a reason for that, which we'll talk about maybe next week. But if you wanted it in, wanted the field in the backside, there's another way you could do it. Let's say something did radiate it in all directions. Well, one way you could do it is by, you have your object in the center here. You could scan a sphere around the object. And then you have a surface with points that you can sum up in any direction, give the pattern in the far field. We'll talk more about that next week. Again, we're still looking for somebody in the Las Vegas area, or somebody who would be willing to come to the Las Vegas area on the weekends to help with this podcast. Looking for a sidekick, I guess. I don't know. Also, if you have any suggestions of what you'd like to see on this, send us an email at suggestions@learningmeasure.tv. If you're a vendor out there of test equipment, we would love to have you on the podcast. Or if you want to sponsor this podcast, send us an email at vendors@learningmeasure.tv. That's it for this week. I'll see you next week.